the organizer for giving me this opportunity to present our research result. Today my report is about the study of ground state configuration of boron 14 via single nucleon transfer reaction. Here is the content. First, let me introduce the background and the motivation. It's why we chose this research project. Okay, for light stable nuclei with small N/Z asymmetry, the existence of the magic number can be well explained by the traditional shell model. However, the increasing N/Z ratios with increasing N/Z ratios, unusual rearrangement of the single particle orbitals emerge in the exotic nuclei far from the stability line. One of the well-known examples is the structure of the ground state of beryllium-11. The stability of one half plus cannot be explained by the conventional shell model, unless we consider the inversion of S and the P orbital. It's also called the intrusion of S of this one, the inversion of S and the P orbital. If we focus on the reason of light nuclei, let's first look at the intruder around n equals 9. For the neutron-rich nuclei with 7 neutrons, the normal configuration is the last neutron occupies the p orbital. Well, as the decrease of J value, we can observe obvious S wave intruder and the D wave intruder. The left finger is summarize the result for the PSD orbital, the ordinary PSD orbital for the n equals 7 isoton. You can see clearly the change of the PSD orbital, and the same trend is also found for the neutron-rich isotopes with 9 neutrons. The ordinary S and the D orbital is changed as the J value change. Okay, for the ground state of n equals 8 nuclei, the zero particle zero hole configuration is predominant according to the conventional shell model. However, the intruder S wave and the D wave configuration has been widely investigated and reported for neutron-rich n equals 8 nuclei. This kinds of intrusion can lead to the breakdown of the magic number n equals 8. For the boron nuclei, lithium-11 this is a well-known boron nuclei. A very large S wave intruder component in its ground state is reported as it's as large as 45%, and this is also proved by proton and deuteron inelastic scattering. The large S wave intruder component is theoretically attributed to the effect of tensor and pairing forces. In the nucleus with one more proton, namely beryllium 12, the S wave component decreases to 19%, whereas the D wave intrusion was found to be dominant. This is the result obtained by our group a few years ago. The sudden change of D wave and the sudden increase of D wave component in the ground state of beryllium 12 may be associated with the pairing interaction and deformation of the core. For the nucleus with even 2 more protons, namely carbon 14, the ground state is composed of only 1.3 S wave and slightly higher, about 8.4% D wave component, which indicates the restoration of the n equals 8 magic number. As the number of the n equals 8 isotonic chain between beryllium 12 and carbon 14, boron 13 offers an intriguing opportunity to systematically understand the neutron shell evolution as a function of proton number Z. That's why we choose to study this nuclei, boron 13. If we neglect the contribution from these 3 half and hyperorbitals and keep boron 11 as the core, the wave function of the neutron wave function of boron 13 can be written as this form. Other experiments have proved that in boron 14 is the last two neutron occupies is the p wave dominant as studied by the magnetic dipole moment and the one neutron knockout. Also, dp transfer reaction also gives a large p wave spectroscopic factor. As for the S wave intruder and the D wave intruder, in a beryllium 14 beta decay experiment, they indirectly deduced 33% S wave. This is very large according to the this is very large. In a charge exchange reaction, they give 24% particle two-hole intruder. This one includes S wave intruder and D wave intruder. But until now, no individual measurements of S wave and D wave species is obtained. So in order to systematically obtain individual S wave and D wave intruder strings, we designed the experiment at Osaka University. We chose this single-nucleon transfer reaction as our experimental tool to study the structure of boron 13. We use CH target and CD target. This is some of the single-nucleon transfer reaction that may happen in the experiment. In the end, we choose the PD reaction and the D-helium-3 reaction to analyze the structure of boron 13, and all the energy spectrum or differential cross section was analyzed with the light particles, that is the helium-3 and the deuteron. Okay, this figure is a schematic view of the configuration of boron 13. We have 5 proton and 8 neutron. If we consider the proton and the neutron elastic scattering, we can use this information to extract optical potential parameters. And if we want to study the neutron configuration, we use PD reaction. We might transfer a D wave or S wave or P wave neutron to the known states of boron 12. If we consider the proton configuration, we can have D-helium-3 reaction. We might transfer a P wave proton. That will naturally give us the positive parity states of boron 12. We should be able to observe the ground state and the first 2 plus and the second 0 plus state. We might even be able to find the third 0 plus or the second 2 plus state. We don't know exactly where they are. Okay, this is the experimental setup. We use 2 plastic scintillators to provide beam particle identification and 2 p-pack to provide the trajectory before targets. And we have 4 sets of charged particle telescope to measure the charged particles produced in the scattering or transfer reaction. Okay, next I will introduce the data analysis and the discussion. First is about the elastic scattering data. We have PP elastic scattering and the DD elastic scattering. We use the elastic scattered proton and deuteron to rebuild the excitation energy spectrum of boron 13. The red finger shows the particle identification of proton and deuteron. You can see they can be clearly identified. And as for the boron isotopes, due to the poor resolution in one of our detector, we can't distinguish the boron isotopes as the proton and deuteron, but we can still see some, this is should be boron 13 and boron 12. This is boron 11. We analyze the after we reduce the excitation energy spectrum, we get down the ground state peak and use the angular distribution of proton or neutron to analyze the scattering differential cross section. This is the scattering data we obtained for proton target and the neutron target. For the proton elastic scattering, we both use optical potential to describe the interaction between the light particles and the boron 13. For proton, we choose WSS global optical potential. We select this. We adjust the depth of this potential to better describe our experimental data. And for neutron elastic scattering, we choose the global optical potential technique and the DAP. The technique is widely used global optical potential. Well, DAP is a newly developed one aimed on the EP shell nuclei. They both give a consistent description of the experimental data. Well, at a large angle of the neutron scattering, we can see the description. This might be due to the coupling or some breakup effects at a large angle. After we have this elastic scattering data, we can use them to restrain the optical potential parameters, and we use them as the input channel parameter for the transfer cross-section calculation. Okay, the next is about the single neutron transfer reaction data. This is the this is the PD transfer reaction. We analyze the reaction products of neutron. This is the reaction produced the neutron. This is the boron isotope. Also, we use neutron to analyze the energy spectrum and the angular distribution. Okay, this is the energy spectrum we obtained from the neutron, the energy and the position information of neutron. We use the known states of boron 12 to fit in this histogram. Because these states have many study about the single particles properties of these states. We just use them to fit the histogram and analyze the different components in the histogram. Okay, this two pictures from the ground state, and the first excited state is formed by the p wave neutron transfer, and this two is from the s wave neutron transfer, and this for d wave neutron transfer there should be 4 peaks, but we didn't. Our resolution is not enough to distinguish them. So we treat this 3 peak as 1 peak and give the sum of the spectroscopic factor. And there are also some P's we have neutron transferred, and here, as you can see, the 2.6 MeV state and the 2.7 MeV state, we can't distinguish them. So we also fit them at 1 peak and analyze their components as 2 components. Okay, then we fit the histogram point by point to obtain our differential cross section. This is for every 4 degree at a point. The peak, the peaks we use here is just the same as the last one. Okay. This is the differential cross section for the ground state and the first excited states. We have 4 points, and the other due to the limitation or acceptance, we have only three points. The best line are theoretical cross sections calculated with DWA calculation. The input channel optical potential is for the input channel optical potential, we use the result we obtained from the elastic scattering, and for the existing channel, we just use the global optical potential technique. Then we extracted the experimental spectroscopic factors with the ratio of experimental cross section and the theoretical cross section. The result is summarized in this table. This is the experimental result. We give the relative spectroscopic factor here. This is the well-known excitation energy. And then I just mentioned we write the neutron configuration in this form, and the normalization relation gives the alpha plus beta plus gamma equals 1. The ratio of alpha, beta, and gamma is given by the sum of spectroscopic factors for the relevant PSD wave transfer. So we can have the PSD wave intensity as 84% and 4% and 12%. In order to compare with the theoretical result, we also perform the shell model calculation with the YSX interaction and the WBP interaction. Here is we listed the spectroscopic factor, the theoretical spectroscopic factor, and to have a more we actually compare the PSD intensities. We make this finger. This is the experimental and the K-shell shell model calculation for the individual PSD wave intensities in the ground state of beryllium 12, boron 13, and carbon 14. The shell model calculation here is with the YSX interaction in full PSD model space. And just for beryllium 12 is from our previous work. The calculation, the measured intensities, you can see the measured intensities for this nuclei can be further reproduced with by the theoretical calculation. They match each other. Okay, this work we have this work submitted to physical review C, and you can read them in archive. Okay, about the single proton transfer reaction. We have the neutron target CD target. We also detect the helium-3 and helium-4 with one of our telescope. You can see this is helium-3 and helium-4. But as for the beryllium isotopes, also suffered from the poor resolution, we can barely distinguish them. And in the analysis of experimental cross section, we choose all of the beryllium isotopes for the calculation. Okay, here is the energy spectrum of beryllium 12. We can observe 3 obvious peaks. That is this is the ground state. Well, around the 2.2 MeV, we observe one. This we treated it as one peak, but it should be the mix of 0, the first two plus state and the second 0 plus state. But we couldn't distinguish them, so we just treat them as one peak and analyze this spectral factor. And above the two neutron separation energy of beryllium 12, we observe a very obvious peak around the 4.8 MeV. This peak is fitted with a Breit-Wigner function convoluted with a Gaussian form function. The width of this peak is determined to be this gradient is determined to be 0.42 MeV. It's very previously in a proton knockout reaction, they also observed the resonance state around 4.7. This might corresponds to that resonance state. Okay, we also analyzed the differential cross section. This is for the ground state, and this might be the another state around 2.2 MeV. They match the theoretical cross section is also calculated with that is also DW calculated. And for the resonance state, the differential cross section is in this finger, in the red finger, and the red dashed line and the blue dotted line represent the theoretical curve for the proton transfer with L equal 1 and L equal 0. The curve for the L equal 1, that is the red one, can well reproduce the experimental data. This is consistent with the experimental result of one proton removal reaction. The L equal 0 proton transfer, that is the blue line, can be ruled out because the shape of L equal 0 curve is inconsistent with the experimental angular distribution. This means populated by an L equals 1 proton transfer from the ground state of boron 13 should be a positive parity state. As I mentioned, this state in the single proton removal reaction, they observed a resonance state with the neutron relative energy about 1.2 MeV. In their work, they didn't assign the parity of this state. But in our work, the excitation energy of beryllium 12 is directly deduced from the present experiment with the missing mass method. With this method, it is not necessary to consider the decaying path of beryllium 12 in the determination of the parity. So we can conclude that this state is a positive parity state. Besides, we roughly analyzed the decaying path. We found that this resonant state will take the one neutron decay. The one neutron decay ratio is about 84%. Based on this character, we think this state should be the 2+ state, but not the 0+ state. Okay, finally is a brief summary. In our experiment, we determined the X and D wave neutron intensity in the ground state and of boron 13 and assigned the steep parity of the 4.8 MeV resonance of beryllium 12. Lastly is acknowledgement. This is our collaborator. Thank them for the support in our experiment and the data analysis process. Thank you.